Hey, what's up guys? Just want to introduce here the singular value decomposition by Rish, Alina, and Julia.
Sometimes the matrix is not an n by n square matrix, like the one shown below, which is a 2 by 3 matrix. So we cannot diagonalize this matrix. We are going to decompose A into 3 parts, which is U, sigma, and V transpose. U is a matrix made of n columns. U sub 1 is 1 divided by sigma sub 1 multiplied by A V sub 1. And U sub n is the same thing but in terms of n. The lowercase sigma values are singular values, which are the square root of the eigenvalues corresponding to A transpose times A. Sigma is a matrix of the same dimension of A, with D in the upper left corner and zeros everywhere else to match the n by n matrix. The next component is V transpose, where V is a matrix with the corresponding unit eigenvectors to A transpose A in decreasing order. This is theorem 9. Rank of A equals R, where A is an n by n matrix and R is the number of non-zero singular values. In this section, there are 4 more add-ons to the invertible matrix theorem.
U is column space of A perpendicular is equal to the 0 vector. V is null space of A perpendicular is equal to Rn. W is row A is equal to Rn. X is A has n non-zero singular values.
Hey, what's up guys? We're going to do a nice little example here, so don't forget our equation. And so we're going to do, first step is to figure out what the matrix is. We're given A, 1, 0, negative 1, 1, 1, 1. First step is to find then ATA, which is 2, 0, 0, 3. And then I always like to find sigma first, which is the singular values. And I get our eigenvalues are 2 and 3. And then I can put them into the matrix and find my free variables. And look at sigma then is going to be D and then however many zeros are added. And so we have root 3 and root 2. And so the dimensions of sigma match the dimensions of our matrix A that we were given. And then we're going to work on V, which is, of course, the eigenvectors. So we have 0, 1, and 1, 0. And then we're going to transpose that. Then we have V transpose.
So now, at this point, we're going to go ahead and find U. So as we know, U is made out of this 1 over the singular value times A times Vn, where Vn represents the vector corresponding to that singular value. So we're going to go ahead and plug in values. So we're going to start off by finding U1. U1 is 1 over square root 3 times A times its vector, which is 0, 1. And that's going to give us 1 over square root 3, 1, 1, 1. Then we're going to do the same thing for U2. U2 is 1 over square root 2, 1, 0, negative 1, 1, 1, 1, 1 times 1, 0. And we get 1 over square root 2, 0, negative 1 over square root 2. At this point, we have to find U3, and U3 is just the null space of AT divided by the magnitude of the null space of AT. So we're going to go ahead and find the null space of AT by setting AT to equal to 0. And we're going to go ahead and row reduce that. So I'm going to actually do the liberty of just doing that without it, and you end up seeing that it goes to give us a vector 1, negative 2, 1. And at that point, we can just find the magnitude by squaring all the values. So we get 1 plus 4 plus 1, and then find the square root of that, and that's square root 6. So the last vector is 1 over square root 6 times 1 times negative 2 times 1. So our final value for U is 1 over square root 3, 1 over square root 3, 1 over square root 3, 1 over square root 2, 0, negative 1 over square root 2, 1 over square root 6, negative 2 over square root 6, 1 over square root 6. And at this point, that's how we decompose it. So we're going to set A equal to all 3 of those components. So E equals U times sigma times VT. And that is our solution. Always remember to circle your answer. And yeah, just leave it in terms of U, sigma, and VT. Give us an A!